Welcome to the online lecture of the course Signals and Systems. Myself Sreekumar G, faculty member, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology. Today I am going to take the topic properties of continuous time Fourier transform. So, before going into the properties, first let us see the equation of continuous time Fourier transform. For a continuous time signal x of t, its Fourier transform is x of e power j omega represented as integral x of t e raised to minus j omega t dt. Similarly, there exists an inverse transform given by x of t equal to minus infinity to infinity x of e raised to j omega e raised to minus j omega t d omega. Now, we see the properties one by one. So, the first property is linearity. So, we have a signal x1 of t whose Fourier transform is given by x of e raised to j omega, x1 e raised to j omega, and x2 of t whose Fourier transform is given by x2 e raised to j omega. Now, we are multiplying x1 of t with the variable with a constant a whose Fourier transform is a x1 of e raised to j omega. Then again x2 of t is multiplied by b, another constant, which gives b x2 of e raised to j omega. Now, we are adding the left hand side a x1 of t plus b x2 of t whose Fourier transform is a x1 of e power j omega plus b x2 of e power j omega. So, this is a statement. Now, we are coming to the proof of this statement. Okay. So, you consider a x1 t plus b x2 t as x of t, and we know the equation of Fourier transform x of e raised to j omega equal to integral minus infinity plus infinity x of t e raised to minus j omega t dt. And substituting the equation of substituting for x of t. So, minus infinity to infinity a x1 of t plus b x2 of t e raised to minus j omega t dt. Now, opening the bracket and giving the integration, we have integral x1 of t e raised to minus j omega t dt with the constant coming out of the integration plus b minus infinity infinity x2 of t e raised to minus j omega t dt. Now, if you look at this, it is nothing but the Fourier transform of the signal x1, which is x1 of e power j omega multiplied by a, plus this is the Fourier transform of the signal x2, which is x2 e power j omega multiplied by the variable b. So, that completes the proof for linearity. Now, we are going to the second property, which is called time shifting. So, time shifting says that for the continuous time signal x of t, if you are giving a shift by t0, that shift will appear as a phase shift. That delay will appear as a phase shift e power minus j omega t0 x of e power j omega. So, the delay in time will appear as a phase shift in frequency. Now, we are going to prove this. So, we know the equation for Fourier transform as x of e power j omega equal to minus infinity to infinity x of t e raised to minus j omega t dt. Now, the signal is the delayed signal, which is x of t minus t 0 minus infinity infinity e power minus j omega t dt. Now, put t minus t 0 equal to lambda. So, we have minus infinity to plus infinity x of lambda, and t minus t 0 equal to lambda. So, t equal to t 0 plus lambda, and also dt is equal to d lambda. So, we have x of lambda e raised to minus j omega. So, t is replaced by t 0 plus lambda, dt replaced by lim lambda. Now, again minus infinity to plus infinity x of lambda e power minus j omega t 0 e power minus j omega lambda d lambda, and the integration is with respect to the variable lambda. So, this is a constant which comes out of the integration. So, e power minus j omega t 0 minus infinity plus infinity x of lambda e raised to minus j omega lambda d lambda. And what is this? This is nothing but the Fourier transform of the signal x. So, which is x of e raised to j omega into e power minus j omega t 0. So, that completes the proof for the time shifting property. Next, we have time differentiation property. Time differentiation property. So, time differentiation property says that I am differentiating the time domain signal x of t. So, that becomes j omega into x of j omega in the frequency domain. This can be extended if you take the second derivative of this signal d square by dt square x of t, then it becomes j omega square. Extending, we have dk by dt to the power k x of t will appear as j omega to the power k x of j omega. Next, coming to the proof. Okay. So, again you take the signal x of t whose inverse Fourier transform is given by 1 over 2 pi minus infinity to plus infinity x of e power j omega e raised to j omega t d omega. Okay. Now, differentiating the left hand side. So, d by dt of x of t. So, you have to do the differentiation for the right hand side. Since the time in this is for e power j omega t, that differentiation applies to only to that part. So, d by dt of e raised to j omega t d omega. Now, doing the differentiation, we have 1 over 2 pi minus infinity to plus infinity x of e power j omega, and d by dt of e power j omega t is e power j omega t into j omega into d omega. Again rearranging, we have 1 over 2 pi minus infinity to plus infinity. So, j omega is written first, j omega into x of e power j omega t d omega. Now, if you compare this with the previous first equation, this is nothing but the inverse Fourier transform of the frequency domain signal j omega x of e power j omega. So, d by dt of x of t is j omega x of e power j omega. So, that completes the time differentiation proof. Next, coming to the frequency differentiation. So, instead of doing the differentiation for time, I am doing for frequency. So, d by d omega of x of j omega equal to x of t multiplied by minus jt. Now, we are going to see the proof. Okay. So, the expression for Fourier transform x of j omega equal to minus infinity to plus infinity x of t e raised to minus j omega t dt. Okay. So, differentiating the frequency. So, d by d omega of x of j omega equal to minus infinity to plus infinity x of t, differentiation with respect to frequency for the term e power minus j omega t dt. So, equal to minus infinity to plus infinity x of t. So, the derivative of the exponent is exponent e power minus j omega t into the constant minus j t dt. Okay. So, finally, writing minus infinity to plus infinity minus j t writing first along with x of t e raised to minus j omega t dt. Now, this is the Fourier transform of the time domain signal j t x of t, which gives d by d omega of x of j omega. So, that completes the proof of frequency differentiation property. And also, I would like to solve a problem of Fourier transform based on frequency differentiation. Okay. So, what frequency differentiation says? Once again, I am writing d by d omega of x of j omega equal to x of t multiplied by minus jt. Okay. So, to find the Fourier transform of the signal x1 of t equal to t e raised to minus 2t. So, looking at this signal, this is of the form t x of t, where x of t is e power minus where x of t is e power minus 2t. Okay. So, okay. So, rearranging this equation, t into x of t equal to minus j to the other side. So, minus 1 by j d by d omega of x of j omega. Okay. So, this equal to minus 1 over j d by d omega of x of j omega. X of j omega is nothing but the Fourier transform of the signal x of t. So, x of t is e power minus 2t. X of j omega is the Fourier transform of e power minus 2t, which is 1 divided by 2 plus j omega. It is the standard form of the exponential signal. So, minus 1 over minus 1 divided by j d by d omega of x of j omega, which is 1 over 2 plus j omega. So, now we have to find the derivative of 1 divided by 2 plus j omega. This is of the form 1 by x. So, 1 by x derivative is minus 1 by x square. So, minus 1 by 2 plus j omega square multiplied by the derivative of j omega, which is j, because we are differentiating with respect to omega. Okay. Then we have minus 1 by j. So, j and j cancels, minus minus plus. So, finally, we have 1 divided by 2 plus j omega square as the answer. So, now we have solved this problem using the property. Usually what we do is that if we have a signal x1 of t equal to t e to the power minus 2t, the natural way of solving is applying the Fourier transform x of e power j omega equal to minus infinity to plus infinity x of t e raised to x of t e raised to minus j omega t dt equal to minus infinity to plus infinity x of t, here it is x1 is t e raised to minus 2t e raised to minus j omega t dt equal to minus infinity to plus infinity t e to the power minus 2 plus j omega into t. Now, we have two variables in t, so we have to apply integration by parts, which will require some amount of time. Instead, if you solve this using the property, you can get the answer easily. So, that is the advantage in using the properties for solving the Fourier transform. So, today we have discussed the following. Today we have discussed the following properties. The first one is linearity, which says a x1 of t plus b x2 of t equal to a x1 of e power j omega plus b x2 of e power j omega. In words, we can say that the Fourier transform of the weighted sum of two signals is equal to the sum of the respective Fourier transforms. Then we discuss the time shifting property, which is x of t minus t0 equal to e power minus j omega t0 x of j omega. That means, if you give a delay in time, it will appear as a phase shift in frequency. After that, we have seen the time differentiation property. So, d by dt of x of t equal to j omega into x of j omega. So, if you do the differentiation in time, in frequency, you have to multiply by the factor j omega. Similarly, if you do the differentiation frequency, d by d omega of x of j omega, in time we get it as x of t into minus jt. So, these are the four properties we have seen today. Thank you.